Hi, everyone. My name's Zane. I realized I actually didn't introduce myself on the first lecture I gave, which was lecture 3, but I'm one of the co-instructors for the course. My name's Zane Durante. I'm co-advised by Ehsan and Feifei. I'm a fourth-year PhD student at Stanford. And in this lecture today, lecture 6, we'll be talking about training convolutional neural networks and also CNN architectures. So, I would say this lecture is really broken up into 2 different components. The first one is just telling you how to piece together all of the different building blocks that we've learned, like convolutional layers, linear layers, or fully connected layers together to create CNN architecture. We'll go through some examples. And then also we'll talk about how you actually train these and all the steps involved there. So as I mentioned before, we'll have basically 2 different topics. The first one is how to build CNNs. And by this I mean, how do you actually define your CNN architecture to set it up to be trained? And then the second set of topics today is how do you train CNNs? So starting with the first set of topics here, we'll go through the layers in convolutional neural networks. And if you recall from last lecture, we learned about the key layer in these models, which is the convolution layer. And the way that these layers work is they have these filters. You have a predefined number of filters per one of these convolution layers, in this case 6. They match the depth of your input data here. So in this case, we have a 32 by 32 RGB image. So we have 3 depth channels. Each of these filters slides across the image and calculates a score at each point. At that location in the image, you take the dot product of the values in the filter with the values in the image. So you multiply all these values together, you sum them together, and then you add a bias term. And this is how you calculate each value in your output activation map on the right. So you have these sliding windows that go across the image. They calculate a score at each position, and that's how you get these activation maps. And you have 1 per each filter. Normally we'll do a sort of ReLU or a nonlinearity activation function at the end here. So this is from last lecture. I won't spend too much time on it. The question is for images, the depth is equal to the number of channels RGB, but here the depth is 6 for the output here. So if we had a second convolution layer afterwards, they would need to be filters that go across all 6 of these activation maps. So the next layer would be a depth of 6. Okay, and then the second layer we talked about, which is much simpler than the convolution layer, is this idea of a pooling layer. So here, it's still this sort of filter that we're sliding across the image, 2 by 2 filter with stride 2. So we're skipping over, we're not doing every single location. And here is a max pooling, so we're just taking the max of each of these areas, and that's the value we get here. Or you could do an average pooling. These are both commonly used, I would say. And depending on the architecture, you would probably just, if you're creating new architecture, you would try both of them and see what performs better here. But the basic idea is to consolidate among the height and width dimensions for your image. Okay, so we've basically gone over, at this point in the course, all the top row here, which is convolution layers, pooling layers, and also the fully connected layers. These are the first layers that we talked about in the neural networks lecture, where it's basically one matrix multiply followed by an activation function. And for the rest of this lecture, I'll talk about the remaining layers that you see in CNNs, at least the commonly used ones, which include normalization layers, which I'll go into those, and then also dropout, which is a regularization technique that's used actually in the model architecture itself. And then finally, we'll revisit the activation functions, and I'll tell you about, here are the most commonly used ones, both historically and in the modern era of deep learning. So starting out with normalization layers, the basic idea here is we're going to be calculating statistics like the mean and standard deviation for our input data, and then using those to normalize the data. And then we'll basically learn what is the optimal distribution for the model to learn at that point. So very concretely, we learn parameters that will scale and shift our input data by a learned mean and a learned standard deviation. So how all of these normalization layers work is there's 2 steps. The first is to normalize the data coming in to be a unit Gaussian, so mean 0, standard deviation 1. And then we will scale and shift it, so multiply by some value to increase or decrease the standard deviation, and then shift it to change where the mean is. And all normalization layers do this technique, but the way that they differ is how they calculate the statistics. So how are you calculating the mean and standard deviation, and which values are you applying these calculated statistics to? But all normalization layers are doing this high-level process. So I'll talk about layer norm, which is the most commonly used normalization layer, I would say, today in deep learning, and it's really commonly used in transformers specifically. And so you can imagine you have some data coming in X, which is a batch size of n. So we have n samples coming into our model, and each of these are vectors of dimension d. So what layer norm does is we calculate a mean and standard deviation for each of our samples separately. So we're calculating what is the mean along the depth or the dimension d here, and what is the standard deviation. Then we learn parameters, and so these are learnable parameters learned via gradient descent in our model to then apply to each sample. So after we calculate our statistics in this way, treating each sample separately to calculate the mean and standard deviation, we then apply these learned scale and shift or parameters here. So we subtract the mean and divide by the standard deviation within our input data to normalize it, and then we apply the scale here with multiplication and the shift. So this is the idea behind layer norm, and at a high level idea, all of these different normalization layers are all computing very similar things. But the main difference is how are they computing the mean and standard deviation. So this is a really nice visualization from a paper called group normalization that introduces a new way to normalize. It's, I would say, not so commonly used these days, but this is actually a really great way to gain intuition about how these different normalization layers are different. So for layer norm, I described the really simple case where we just have vectors that we're normalizing. But in the case for convolutional neural networks, we have channel dimension or the depth. We have in the height and the width or the spatial dimensions of the image. So what layer norm does is for each sample, we're still processing it separately, and we're calculating the mean across all of the channels, all of the heights, and all the widths. So if we look sort of back into this diagram here, you would basically be calculating one mean and one standard deviation over all of these values. So for each of our input data points, we're calculating one mean and one standard deviation across all of the channels, all of the height and width dimensions. So this is what layer norm is doing. But you could imagine feasibly that you could calculate these statistics differently. Batch norm, you're taking each channel. So each channel is being calculated as one mean and one standard deviation, and you're applying it just to that channel. And so you're averaging across all the data in your batch. Instance norm is even more granular, and then a group norm. So I just want to point out all these layers are kind of trying to do the same thing, where you're basically normalizing your data and then having these learnable scaling and shifting parameters, but the way they do it is different because they're calculating the statistics using different different subsets of your input data. Yeah, so the question is for layer norm, are we calculating one mean and one standard deviation for each image or input data? Yes. They're all calculated separately. But for batch norm, it would not be the case in this example here. Yeah. For batch norm, it's actually within the mini batch. When you're doing gradient descent, you have a small batch of data you're looking at. You feed it into your model. You're calculating the per channel mean and standard deviation based on all of the data in your batch. Yeah, I think this is like a good, if you can understand this diagram, I think you understand what all of the different normalization layers are doing. So it might be worthwhile after lecture, if you still don't fully understand it, just to go through and make sure you understand what, and shaded in blue, these are the values we're both calculating our statistics over and then applying the mean and standard deviations to. One final question and then we'll go on.
Is channel same as like the layers?
So channel here is the depth here. So the number of spatial the different spatial values you have at each the number of values you have at each spatial location. Okay, cool. So this is, we talked about normalization layers. The key idea is you're calculating these statistics, applying them to your input data, and then learning a scale and shift parameter that you then apply. So the next type of layer we'll talk about is called dropout. And this is a regularization layer in CNNs. And this is the final layer that you'll need to learn in order to basically, we can start going through all these different CNN architectures that people have created over the years. So with Dropout, the basic idea is to add randomization during the training process that we then take away at test time. And the goal is to make it harder for the model to learn the training data, but then it will generalize better. So this is a form of regularization. The way we do it concretely is that in each forward pass of our layer, we'll actually randomly zero out some of the outputs or activations from that layer. And the main parameter you have for this dropout layer, which is just a fixed hyperparameter, is the probability of dropping out the values. And 0.5 is probably the most common, or 0.25 is also commonly used here. So you're just dropping out a fixed percentage of the values here. And so, going forward to the next layer, these would be 0. And so you don't really need to calculate the values here. So, basically all the outputs here are 0 at this point. So you can there's some tricks you can do with masking, so you don't even need to calculate the values, because 0 times any value will be 0. So, I think in general, you might ask, why does this work? And, I would say this is more of an empirical thing than a, well studied from a theoretical standpoint. But there are actually some ways you can view what Dropout is doing to gain intuition of why this might be useful. So it basically forces your network to, you can imagine it forces it to have redundant representations. So if we have a list of features that we're learning at a given layer, say the layer right before the output of our model, and we have a CNN that is basically extracting each of these features. So it can detect if there's ears in the image, or if there's a tail, if it's furry, it has claws, and you want your model to output the probability of a cat score. So one of the things that's useful about this is, because some of these values might randomly be dropped out during training, your model can't over-rely on certain features being present in some of the classes, and actually needs to learn a more broad set of correspondences between your features and your output classes. So the model can't just hard focus on, okay, well, if it has an ear and is furry, these are it just so happens that these are always cats, or something like this. Or if it has claws, and it has an ear, it'll almost always be a cat on your data set. So it'll actually help you generalize better to new features, despite the fact that in your data set, there might actually be really strong correlations between the codependency of certain features in your output class. By having Dropout, you're essentially making it so the model can't rely on these during the training phase, because it won't always see the pairs of features together. So this is an example for cat. And the question is, if we had something like tree instead, how would you determine which features to drop out? So the dropping out part is actually completely random. So we're not making any choices about this. It's just, in this case, 50% of your features at any given step will be dropped out and set to 0. Yeah, you don't have to make choices about it, which is kind of nice, but it is completely random. How would the model know if you're only seeing a subset of the features, like tail and claw here? The point is, you will actually do worse on the training data because you're only seeing a subset of the features. So it does make the model worse by not having all the information. But then it does better at test time is the idea. So worse in training time and better in test time, because at test time, you're basically no longer having this dropout. So the final component here, which maybe I should have explained first before fielding questions, is the idea at test time, you're no longer dropping out any of the values. So this is randomness that we're adding during the training phase only. Then at test time, we're never masking any of the output activations, and we're removing this dropout idea altogether. Now, one thing we need to note is that because if we were dropping out 50% of the activations during training time, at test time, you're basically having 50% more values that are being input to each of your layers. And so this can cause issues if you don't scale it. So what you need to do is multiply by the probability of dropout so that the sort of magnitude of the values coming into each layer is preserved during training and test time. Otherwise, if you're dropping 50% of the values and then at test time you just include all of them, you'll get really weird behavior because you'll be seeing much larger magnitude of inputs than before. Yeah, so what about for backward prop? So for back prop, when you have these zeroed values, yeah, it's sort of like you don't need to traverse that path of your directed graph anymore. It's very similar to ReLU. If you have a zeroed value at that point, the gradient becomes 0. So anything sort of further back in your computational graph, there's no gradients calculated at that point. If you're dropping out certain values or activations, the weights associated with those specific activations will not be updated during gradient descent if you're dropping them out. Yeah. So the question is, maybe I'll reframe it. What are we doing at test time? So at test time, we are using all of the output activations. We're not dropping them out anymore, but we need to scale by the probability of dropout. So we multiply each of our output activations by this p-value because now we're using all of them. So otherwise, you can imagine you have each node is sort of seeing a significantly higher number of inputs than it did during training at test time. So you need to multiply by this p-value to maintain the same magnitude of your inputs coming in, and the variance stays the same and all these different properties. It works very nicely if you do it like this. Yeah, so the question is, can you just add noise to the image instead? The answer is yes, and we'll go over how to do that in future slides. Yes, that's a great idea to add noise to your image. Okay, some specific code here. I won't go over this because we already mentioned this, but you're dropping a p percentage of your activations here, and then you multiply here at test time. Okay, the next topic I'll talk about is activation functions. So you all have basically learned all of the key layers now in CNNs, and now we're going to be talking about these activation functions. If you remember, the whole point of these activation functions is to introduce nonlinearities to our model. So right now with these convolution operators, the kernel sliding across the image, and the simple layers without the fully connected layers without activations, they're all just linear operations because they're multiplications and additions. And the whole point of the activation function is to add nonlinearity. So historically, sigmoid was a really commonly used activation function, but there's actually a key problem with sigmoid that is the reason why it's no longer used today. And so sigmoid, if you graph it, looks like this. You can see the equation in the top right of the slide here. And the main issue is that empirically what happened was after many layers of sigmoids, you would get smaller and smaller gradients as you're computing backprop. So starting from the end, the gradients are fairly large in magnitude. And as you undergo multiple layers of backpropagation, go to the initial early layers of your model, you would get smaller and smaller gradients as you do this process. So I'll actually open this question up to the class. This isn't a phenomenon we see that occurs with sigmoid. And so in what regions in our graph does sigmoid have a really small gradient? Yeah, so very negative and very positive values is correct. And this is actually a huge issue. I mean, you can visually see here in the graph, the gradient's very flat. You're taking the derivative here, it's very small. And so basically for almost all of our input space, from negative infinity to positive infinity, you have very small gradients. And it's only this narrow range in the middle where you have something that's non-zero. So it basically approaches zero very quickly on both ends of the extremes. And so this means that if the values coming into sigmoid are very large or very small, then your gradient will be very small. So this is one of the main reasons why ReLU became super popular, because now in the positive region, we don't have any of this behavior. It's just a derivative of 1 here. But in practice, you still have this flat portion here on the left where your gradient is 0. So now we basically have half of our input domain here. We get a gradient of 1 and the other half is 0, which is better than almost all of it being 0 or very close to 0, except for a small region in the middle. So in practice, these work better. Also, it's much cheaper to just compute a max operation between 0 and your input value than the sigmoid function. So for those two reasons, ReLUs became super popular. But you still have this issue where for any negative input, you get a 0 gradient. And so, more recently, there's been, popular activation functions that avoid this, by basically having a non-flat section of the activation function in the nearby neighborhood, to near 0. So, this is GALU, and there's also CLU, which I'll show in a slide, but I won't go over the formula. They look very similar. The basic idea is to smoothen out this non-smooth jump here in the derivative from 0 to 1 at 0.0 for ReLU. So, there's a very sharp and non-smooth function with ReLU, but the nice part about GALU is we actually have non-zero gradients here, and in the limit, as x approaches infinity or negative infinity, it does converge to ReLU as well, but you get sort of more smooth behavior in the middle here. And specifically what GayLU calculates is this Gaussian error linear unit. So this is the cumulative distribution function of a Gaussian normal. So if you imagine the area under the curve of a Gaussian, that's what this phi of x is at any point x. So if you have a really negative value here, you'll have a value close to 0, which is why it sort of converges to ReLU 0 here. And at a very high positive value, it gets very close to 1, the area under the curve. So it converges to x here. So this is GayLU. It has these nice properties, and it converges to ReLU at the extremes too. And this is the main activation function used in transformers today. If you look at all of them and you kind of squint, a lot of these kind of look the same. The basic idea is something relatively flat, and then in the limit, it approaches f of x equals x, and sort of it becomes a linear line. So CLU is actually x times sigmoid of x, which also has this property of, for a very negative value, you have something close to 0, and for a very positive value, it's close to 1, so it's actually similar to the cumulative distribution function for the unit Gaussian that is phi here. So that's why the shapes are actually really similar looking too. Okay, so you might ask, where are these activations used in CNNs? And the general answer is that they're placed after linear operators. So almost any time we have a feed forward or a linear layer or a fully connected layer, these are all words for the same layer. It's a matrix multiply followed by activation function. Or if we have a convolutional layer, pretty much after these is where we place so after the convolutional layer or after these linear layers, we'll put the activation function. Okay, so you've learned everything now about all the components of CNNs, and I'll now go through some examples of how we put them together and how people have created state-of-the-art convolutional neural network architectures. I think this is a really neat slide because it plots two different values. So on one hand, we have the error rate, which is these blue bars, and this is over time. So these are different models people have trained on ImageNet. And then you have these orange triangles, which represent the number of layers that models have. And you can see at the same point that we have a significant drop in error, where we actually surpass human performance for the first time, we see a huge increase in the number of layers. So we'll go over in class today how they were able to achieve this and what were the design challenges and goals for how they did this. Historically, AlexNet was the first sort of CNN-based paper that worked really well on ImageNet, and they were able to train it by using GPUs. We talked about this earlier in lecture, so I won't spend too much details around AlexNet from a historical lens, but I do want to compare it to another architecture called VGG, which was a really standard and commonly used architecture in the 2010s. And I think I can plot the two CNN architectures together side by side here. So in general, in AI, we like to plot our model architectures using block diagrams, where each block represents a different layer or a group of layers that are stacked together. And it also helps you gain intuition about, what are the general differences just at an initial glance. So these orange blocks, which are the common ones here, are 3x3 convolution layers. So these are convolution layers that have filters that are sliding across that are size 3x3. Their stride is 1, so they're visiting every location in the image, not skipping over anything. And they add padding of 1 around the outside so that we're not shrinking as we do these convolution layers. And so they also add these max pooling layers throughout here too. And you'll notice that for all of these, they have, after a pooling layer, they'll start doing 2 sets of fully connected layers of dimension 4096, followed by a dimension of 1,000. And the reason we have 1,000 at the end is because ImageNet was 1,000 different image categories. So we need to have scores for each of these categories. So the final layer is always equal to the number of classes you have for an image classification problem. And so you can see it actually looks extremely similar. It's sort of just like a scaled up version of AlexNet with more layers here. And also they're now doing some sort of 3 groups of convolutions at a time followed by pooling rather than 2 layers in a pooling or even 1. So it is actually pretty remarkable that there's only basically 3 different types of layers, right, in these models, but they perform extremely well compared to anything people had tried before at this point. So these are, I would say, the simplest layers. You might, simplest models we're going to discuss today, but you might ask, why are they doing 3 by 3 convolutions? Like, how do they pick this value? And there is actually some intuition behind how they chose 3 by 3. So and specifically, they have groups of 3 or even 4 of these. So I'll ask you all a question. What is the effective receptive field? So we looked at receptive field last time, but it's basically the idea of the parts of your input image that a particular value in your activation map has seen before. So what values have been used to compute the final activation map after many layers of your model? So you have 3 of these layers that are all 3 by 3 convolutions with this sliding filter with stride of 1. What is the effective receptive field of each value in our activation map A3 here? So this is after the 3rd layer. So I'm showing one of the layers here. You can see for each value in A3, it's computed by looking at a 3 by 3 grid of values in A2. And then conceivably for each one in A2, it's a 3 by 3 grid in A1. And for each of those, it's a 3 by 3 grid in our input. So I'll let you all think about this for a little bit. Maybe it will help to see the next layer here. So it is actually really helpful to visualize this. So at A1, each of the corners here, we're calculating from a new 3 by 3 grid here. So from our input, how large is this overall square? 7 by 7. Yeah, exactly. So this first one is 3 by 3. This next one is 5 by 5. And then the next one is 7 by 7. And we can visualize it here pretty easily. So the nice thing about the 3 by 3 convolution with stride 1 is that you're basically always adding 2 to your receptive field at each layer because, each point here, you're looking to the left and to the right and above and below it. So after you have many blocks of those, you're just adding 2 each time. Okay. So we basically just showed that a stack of 3 of these 3 by 3 convolution and stride 1 layers has the same effective field as one 7 by 7 layer. Yeah, so the question is, how much of this is justification after the fact versus how much of this is intuition that they then use to, say, design the experiments? I think it actually probably depends on the architecture. So for some of them, it's more intuition focused. And actually the one we're going to cover next, I think really was the whole research direction was spawned by an empirical finding that there's a thought experiment about. So that's ResNets. And I think there's actually pretty good intuition that led the whole investigation into what will work well. But then for this one, I can't speak for the authors, whether it's justification after the fact or, based on empirical findings or if it was involved in the design choices, because I haven't seen them speak publicly about that yet. But for ResNets, I do know it was the hypothesis that led to the creation. But this is actually a really nice property. So 3 of these 3 by 3s have the same effective receptive field as one 7 by 7 layer, and it actually has fewer parameters too. So we have, if you imagine our channel dimension is staying the same, you have these 3 by 3 grids where you have your input number of channels. So 3 times 3 times C would be the number of values in each of these filters. And if we have C of these filters, it's 3 times times C or 3 squared C squared. And we have 3 layers total. So, sort of if we look at it through this lens, it's actually fewer parameters, and we're having a more complex, and more nonlinear model that we're building here. So fewer parameters, and it can model more complex relationships among your input data. So this is maybe why stacking these 3 by 3 layers together could be better than having just a larger filter that you're sliding across. So fewer parameters, and then also you can model more complex relationships. Okay, I'll now talk about ResNets, which I guess I'll very much bring up the thought experiment that someone just asked a question about. So there was actually an empirical finding that spawned a lot of the conversation and thought around designing ResNets. And the idea was actually shown that if you keep stacking deeper layers on a plain CNN network, like something like this, and you just keep adding layers to it, you build it larger and larger, what happens? So what we found, and what they found, is that The 20-layer model will actually have a lower test error than a 56-layer model. And you might think that this is because of overfitting, but it's actually not, because if we look at the training error of this 20-layer model is also lower. So it has a lower training and a lower test error. Basically means that the model is doing better on all accounts. So why is this 56-layer model performing worse than a 20-layer model? It doesn't, it might be confusing. And we know, as I mentioned right before, it's not caused by overfitting. So these deeper models have more representational power, and theoretically, they should be able to represent any model that a more shallow network can model. So the set of possible mappings between your inputs and different values for your larger networks is a superset for your smaller networks, because theoretically you could imagine that you basically are just setting some of these layers to be the identity function, where the layer's doing nothing. And then you would have, if you set half your layers to do nothing, you have exactly the same representation power as a model 1/2 the size. So the idea is not that these models are worse, but in terms of the representational power, but they're actually harder to optimize, because the set of possible models for your deeper networks is larger, and it contains all of the possible models that your more shallow networks could learn. So I sort of hinted at it before, but how specifically could the deeper model learn to be at least as good as a shallow model? It's by setting, so if we have a 2-layer model versus a 1-layer, so 1 layer here and 2-layer on the right, if we set one of the layers to just essentially be a identity matrix, or, this is just an identity function, the model should be at least as good as the shallow model. It should be at least as good as the shallow model. So how do we actually build this intuition into our models? We want them to be able to be just as good as a shallower model if they want to be during optimization. So the way that we do this is actually by fitting what's called a residual mapping instead of directly trying to fit a desired underlying mapping. And what this looks like is we basically take the value x and we copy it over past our convolution layers, so that the value at this point is already receiving x, our original input, as well as the output of our 2 convolution stacks. So basically at this point, this f of x, or which is called the residual map here, it could just learn 0 values for all the conv filters, and the output would be 0 here, and then we would just add x along here, and we would get x. So it allows a very simple way for the model to bypass these layers if it doesn't need to learn anything for the layers. And what this means is you can really easily now learn basically this identity function that we talked about earlier by just learning zero filters. So your filters all are filled with 0 values, for example. Or in this case, more practically what happens is they just need to learn very small values, because instead of learning this entire mapping from x to h of x, they just need to learn this difference, which is f of x. So you're now just learning this sort of difference between your desired output here and the copied over block. This is called residual block, or residual connection, when you copy over values from an earlier layer into a later layer in your model, and then you just add it to the values at that point. So I talked a bit about the intuition, which was this observed phenomenon that these larger networks were achieving worse training and worse test error because they were harder to optimize. So the intuition was we need to build a model that can really easily model the shallower networks, so it can be at least as good as a shallower model. The way they did this was by adding a residual connection so that you can just copy over the values easily, build that into the architecture itself rather than trying to learn some identity mapping among the convolutional layers. And empirically, this showed to work extremely well, too. Yeah, so what does the residual block carry? So we have our input x, we pass it through 2 different convolution layers, and we get our output f of x. X is just copied over here. So this is exactly the same as x, and we add it to the output of these 2 blocks, which is f of x. Yeah, x is the output of one of the previous layers, or if it's the very first layer of the model, it would be the image. Yeah, so the question is if maybe you just don't have enough data, and if you added enough data, then maybe you could train a model without these blocks. I think these blocks actually do extremely help you with learning from more data. I think the issue, it was really an optimization problem. So transformers use residual blocks for exactly the same reason, because, and I think it actually helps you model these more complex models, and it actually enables you to use more data. So I think that it's very good. Residual blocks help you use more data more efficiently because you're able to model a greater number, or you're able to more easily model a greater number of functions. Yeah, so the question is that maybe if we just trained for longer, the performance would eventually converge to the value of the smaller network, and maybe it's just harder to optimize because it takes longer to train a larger model. And I think the answer is no, that these were not, they were not converging to the performance of the smaller model, regardless of how long you trained it. And the reason is because it's being stuck in essentially local minimum, and when you add these residual connections, you're avoiding these. This is the actual explanation. Why this is the case is still, I would say, being a more active area of research. It's really hard to understand exactly what causes these models to avoid global minimum, to avoid local minimum and not get an optimal solution, or to what causes them to not train and find better solutions. And oftentimes this is really an empirical finding, but there's some intuition behind it. And in this case, the intuition was that we want to enable our models to do at least as well as the shallower models, which we know were performing better at the time. So it's not that you could just train it for longer and it would do better. It was actually a limitation where it was no longer, it was just completely unable to achieve as good as the shallower models. Okay. So here's the overall ResNet architecture. We have these stacks of residual blocks now. So that's what these two blocks here together mean. It's a residual block. So we have a 3x3 convolution with the ReLU followed by another 3x3 convolution. And we're copying over this X value here. We're adding it to the outputs here. And then we're having a ReLU afterwards. So each of these pairs of blocks is one of these residual. And that's why you see this line skipping over here, because the value is getting added forward. The cool thing about ResNets also is that they basically had a lot of these different depths that they created. So they created a whole family of models, some smaller and some larger. And they showed that as they increased the number of layers, their performance was increasing, albeit the sort of the difference in performance as you got to the larger and larger models became smaller. So it was sort of reaching a point of, given the data set, they weren't able to scale any significant amount by adding more layers further than that. But they saw significant improvements in performance among, especially the earlier models. And then 101 to 152 is where the performance, it wasn't really changed. It was marginally better, but performance changes maybe only like 1% at that point. Yeah, how did they get the number of 152? I actually don't know how they got the number of 152. I think they wanted to try different values here. And you can see that, I mean, they're not exactly doubling, but, it's sort of, a significant increase in each time. I don't know how they picked 152. That's a good question. Maybe they showed it somehow worked better than other. I actually don't know though. So generally when you're trying multiple different number of layers for your model, like given that, say, these are the number of layers you want to try, what you'll do is you'll sort of first train the smallest model, see performance, and then add more layers, see if your performance increases, and go on, so forth. So that's probably why they stopped at 152, is because performance wasn't increased as much anymore. And also there's GPU memory limitations. So as you get larger and larger models, it becomes harder to train from a hardware perspective because you need to fit more parameters into your GPU memory. So there is like a limit for, given your compute setup, how large of a model you can train. I think you need to train these models separately though. So you have one model run for 18 layers and one for 34, et cetera. So the question is how to think of intuition of CNN blocks given we're using these residual connections, because you can still think of it as higher levels of abstraction, and this is shown to be true in the layers. So you're not, instead of learning within the block itself, instead of just learning the higher level features, you're learning the delta from the original image to get the higher level features. That's what you're learning in the block. So you're learning the delta, but you're still achieving these higher level representations at each step. So that part is the same, but the actual functional way of doing it is we're learning this, right? You learn this f of x that you add your previous input to. So it's like you're learning the delta. The question is, if you do addition, does that require you to have the same tensor size? The answer is yes. And, it's part of the reason why it's really a nice property that all of these ones have this 3x3 convolution with stride 1 so that you maintain in one padding, so that you maintain the same size, at every layer going forward. So after you had, say, a pooling layer, you could maybe come up with a way to do it where you double you increase, you sort of unpool the values. But after a pooling layer, for example, you couldn't do a naive addition anymore because the size of your tensors are different. So these are done within, before a pool. At least the regular one. I mean, you could get around it by just having each value be spread out into multiple values, for example. Okay, so these are basically the main takeaways for ResNets. One other neat trick they do is they basically periodically, after a certain number of these blocks, they'll double the number of filters and downsample the spatial dimension. So basically, you can imagine if you start with a really flat image, as the activations get pushed through the network, it becomes smaller spatially, but then the depth is larger. So this is how to think of it. And then at the very end, it just becomes a vector that you then use for classification. So that's how you should be visualizing what's happening to the values in the network itself and the shape of them. And then one other sort of thing that's somewhat unique to ResNets, other architectures do this too, but before all these layers with the residual blocks, they have this relatively larger convolution layer. And here is just empirically shown that it did better if they added this here. So this one is purely empirical finding. Okay, I think, basically to highlight, it did extremely well, these larger models. It was the first time they were able to train 100+ layer model successfully. So it was a really big deal. And basically ResNets were used in a huge variety of computer vision tasks afterwards. Almost every task in computer vision was using a ResNet at the time because they performed so well because of these residual connections. Okay. So we talked about some CNN architectures, the main one being ResNet, and then also VGG historically. So we talked about why the smaller filter size is useful, and having many layers of these is useful. So the final thing I'll talk about in terms of how we actually construct the CNNs and prime them to be ready for training is how do you actually initialize the weight values of the individual layers? So, depending on what values you choose, you could either put values that are too small or too large, which would cause significant issues for your model during training. So here it's basically a 6-layer network where we have 4096 dimensional features, and this is just 6 layers of fully connected model. And we initialize them. Here, this is getting unit Gaussian random, and then we're multiplying it by 0.01 to get very small values close to 0. And we have, ReLU at each layer too. So if you plot the forward pass of this model, you would actually see that at the beginning, you get relatively high, because there's ReLU, so all the means are going to be positive, but you'll have a mean and standard deviation that is relatively high, but as each layer progresses, because we had a really small weight initialization, it becomes smaller and smaller mean and standard deviation. And really ideally, we would want basically all of these to be the same for each layer, because it makes our optimization problem much nicer to solve. So if we say use 0.05 instead of 0.01, can anyone imagine what might be the issue here if we set it to too large of a value? So when it's too small, it goes to 0 basically. What happens if it's too large? Yeah, basically the activations get larger and larger at each layer. So if you plot it here, you can see that, by the end, there's just a massive mean and standard deviation. And if you're training a 152-layer ResNet, and, you can imagine this becomes quite an issue very quickly. So how do you actually do this? So in this case, maybe the optimal value, I think, is 0.022 or something. But how would you actually know that? And how would you do this more generally across any layer? There are a few different ways you can initialize weights. And I'll go over the most commonly used one today in class, but no, there are other ones. And generally, what they're a function of is the dimension of your of your values here. So you'll have a different value for a 4096 dimension, fully connected layer versus a 2048. And the specific formula we'll go through, is called Kai-Ming initialization. It's actually the same person who created ResNets. So Kai-Ming He, he was, very famous. I mean, he still is a very famous computer vision researcher. I think he's one of the most widely cited computer scientists of the last 10 or 15 years, maybe the most. So he's extremely well known in the computer vision community. And he also came up with this idea of initializing the values to the square root of 2 over your input dimension size. And I won't go over all the details for how they derived this and showed that with a ReLU activation, this would cause the standard deviation and mean to be relatively constant throughout the layers. But if you do plot it, you see this does have the effect. So you can almost think of this as a magic formula where if you plug it in, you get the desired properties. And if you want to know the derivation, you can actually, we linked the paper here, so feel free to look into that. But you can just sort of take our word. I won't go through the details here, but it does this desired effect where the mean and standard deviation is unchanging. And you can also imagine that for any given setup, you could also just through testing try to find what is the value here. Okay, so these are how we discussed how you initialize weights, how you combine these different layers together to form a CNN architecture, which activation functions people use, and then all the different layers in CNNs. So I think already we covered quite a few topics. So I think I'll pause very briefly to see if there's any questions about these. In the second part of the lecture, it's actually much less dense than the first part. So we'll be mainly going over a lot of nice practical tips for when you're training these models. So the question is, how do you do weight initialization for CNNs? So you still use this same initialization, but your dimension in here is the size of your kernel. So if you have a 3x3 kernel with channels, say 6, it would be 3 times 3 times 6. But it's the same idea. It's just you calculate your dimensions differently depending on the type of layer. Yeah. You can think of it as the number of values roughly in each operation. But it does depend on the layer. And some layers use different weight initializations, but this is specifically for CNNs, how this Kai-Ming initialization applies to it. Yeah, so the question is, why do your activations explode if you have too large of an initialization value? So you imagine at each layer of your initialized network, you have a set of randomly initialized values, and if they're very large, then when you do your you have a ReLU activation afterwards, and that doesn't actually cap the outputs of your layer, right? You can go to infinity with ReLU. So if you have too large of a set of values that you're essentially repeating the same operation on because you're initializing all the weights to the same set of random values, then at each layer you'll be multiplying one set of large values by a set that's been initialized too large, so that it becomes larger at each iteration afterwards. I mean, you could think of it as it's sort of like a recurrence relation where, because they're all initialized randomly at the start, where it's being multiplied by a value, and you would want, in a simple recurrence relation, you want it to be 1, right? But because we have a vector of values that are being multiplied by our matrix, it depends on the dimension of the vector, what your average output would be, and what the after the ReLU, because you have basically a standard deviation for what is your activations, then you remove all the negative ones, and you're left with what are your outputs at that point. And if you have a really large values, you have a really large standard deviation. So when you remove the bottom half of it, you get your mean starts moving more positive and more positive. Did that make sense? It's sort of, I didn't have slides to show it, but okay, mostly, sorry, yeah. You can see more details in the paper. It's actually not too bad to read, I think. So the conclusion of the discussion here is that normalization would solve this activation issue where they're blowing up, but it still might be harder to optimize. Maybe we should probably do a follow-up post on it explaining this in more detail, but I think it's a really good question, actually, yeah. It would solve, I think, this particular issue, but maybe it's still hard to optimize like this in the discussion. Yeah, it's a good question. Okay. Cool. So I'll talk about these steps now. So how do you actually train your model? And the nice thing for data preprocessing is it's really easy for images. So if you have your giant image data set, the standard way to do it is you calculate the average red, the average green, and the average blue pixel, along with the standard deviations. And you take your input image, you subtract the mean, and you divide by the standard deviation. And this is how you do data normalization for images. It's actually very straightforward. So it does require you to pre-compute the means and standard deviation for each pixel channel. So sometimes what people will do is they'll use means that have already been calculated. Like a very common one is to use the ImageNet means and standard deviations and apply those to your input images, even if you're training a model not on ImageNet. So it is very data set dependent is the way to think of this. And different models will use different values here depending on their data set, but the most commonly used one is just use the mean and standard deviation from ImageNet. Yeah, so any input image, you've applied this operation before the model sees it. Okay. So yeah, that one was really quick. And then in terms of data augmentation, so someone had a suggestion earlier in the class, why don't we just add noise to our image? And that's a great idea, and we'll talk about the different ways you can add noise to your image here. This helps with regularization and helps prevent your model from overfitting. So we talked about it before, but this is sort of a common pattern with regularization where during training time you add some kind of randomness, and then at testing time you then average out the randomness. So sometimes this is approximate, but for example, for Dropout, we saw that during training time we'll randomly drop, say, 50% of the activations, and then at testing time we'll use all the activations, but then we'll need to scale it down by this probability of dropout p. So this is a really common pattern, and it's also used for data augmentation. So you can imagine this being this cylinder here is like your data set. You load an image and a label. So we have a cat label, and we have our original image from our data set. Before we actually pass it into our model, it's extremely common, and basically always in modern deep learning, people will always use data augmentation for training computer vision models, but the basic idea is to apply some transformations to the image to make it look different, but still recognizable for the category class, and then pass that to your model, and you're computing the loss here. So one of the nice benefits of this is you can effectively increase the size of your data set, because instead of seeing each image multiple times, it will be seeing different versions of the image with different transformations that all still are the same category label. So you can basically get more data, and therefore it increases your generalization capabilities, but your training loss will be higher because you're not just seeing the same example over and over again. So it makes it harder for the model to just memorize. So how do we know the weight initialization is just right? So we know it's right in this case because the means and the standard deviations are relatively constant throughout the layers of the network. And we're not seeing, in this case, we saw sort of mode collapse to 0. In this case, it was sort of blowing up to infinity as we increase the number of layers. So the way you can ensure it always happens is by using the formula. This will always initialize them well. So in practice, that's how people do it. If you were creating a new layer that maybe does some different kind of operation that no one's done before, then you probably would need to try a bunch of different weight initialization schemes and see what works best. But generally, for these linear layers or the convolutional layers, you can use this formula here, which is called the Kyming initialization. Yeah. Okay. So back to data augmentation. So what are the different augmentations you can do specifically? So one of them is horizontal flipping. This depends on the problem. So if you want to have a model that reads text, this would be a very bad augmentation to use because the text is now, it's like you're looking through a mirror and you can't read it properly. So this isn't sometimes useful for everyday objects. It's usually pretty good because most objects are symmetrical, so this property actually works pretty well. And then you could also imagine if you're looking maybe at images from a microscope or overhead that you could also do a vertical flip, and that would make sense. But for everyday objects, vertical flipping actually doesn't really make sense because a cat is almost always seen in this position. But maybe if you had a data set where cats were in all different orientations, you could imagine that flipping or rotating or all these things would make sense for your data set. Another type of augmentation is this resizing and cropping idea. So what ResNets and many different image models and deep learning do is they basically take a random crop of the image and then resize that to be your image size. They might even take another crop afterwards. So the most common strategy is you pick the length of what is basically the short side of your image. So if you have a input image size to your model of 224 by 224 pixels, you would pick a value larger than this first and find some crop of your image that contains this larger scale L. And these are commonly used values. You crop the image. You don't crop. You resize the image to be that scale. So instead of, say, this is an 800 by 600 image, if we use 256 here, we resize the short side, so 600 to be 256, and then 800 would be scaled correspondingly. So we scale it to this L, we scale the short side to L, and then we crop a random patch of 224 by 224 pixels from that image. So you're scaling the image by first you preserve the relative resolution, but you make it smaller or larger to fit this L, and then you take a random crop of that. And this is like by far the most commonly used random resized crop is what it's called in most libraries. So this is used in most problems because it works pretty well, and it reserves the relative resolution of your images. And then there's another neat trick you can do with augmentation called test time augmentation. So if you really just want to get the best performance possible, you can basically get a bunch of these different crops and resizes and run them all through your model and then average your predictions at the end. And for ResNets, people will often try a bunch of different scales, a bunch of different crop locations, and maybe even flip it. And usually you'll start getting diminishing returns, but you can get actually pretty good, like 1% to 2% performance boost by using this sort of test time augmentation. So if you're in a setting where it really matters, you're trying to eke out every last bit of percentage points, then this is actually a really great trick that you can use for almost any computer vision problem. Okay, so a final sort of few augmentations. One is color jitter. So here we're specifically randomizing the contrast and brightness and scaling the image correspondingly. So maybe images look more muted or the colors look more muted or more brighter, but these are sort of very traditional image processing techniques. And usually with all these different augmentations, you'll try different values and see which ones make your images still look in distribution and look normal to you as a human. And that's like a pretty good way to judge what values you should pick for how much jitter you should have, how much brightness variance, etc. So normally when I'm starting a problem, I'll try a bunch of these different augmentations. I'll see what is making the data look different from the original data, but then still recognizable to me and still very easy to recognize. And that's like generally a good set of augmentations to use. Final one is you can imagine just like cropping out parts of the image where you just are basically putting a black or a gray box over it. And I think this one's maybe less commonly used, but it kind of shows you how you can get creative with the augmentations depending on your problem. Like say you're in a setting where things will get covered, like the camera will be occluded, so it won't be able to see the objects fully. This could be a really neat trick you do to make your model more resilient to stuff blocking parts of your objects. So you could almost imagine for your given setting what augmentations make sense, what ways can you transform your input data so that it's still recognizable to you as a human, but it makes it harder for the model to memorize the training examples. Okay, so the final set of topics here are basically extremely practical. So when you're, say, doing a project or training a model, so say for your course project, I think you should basically do the exact things we're going to be describing in the coming slides. But this also applies outside the course to any computer vision domain you could be practicing in. So in practice, in many times, we don't actually have so much data. You know, ImageNet, the original version, had 1 million images. Maybe you don't have 1 million images for your problem, which almost none of us do unless you've been collecting a vast amount of data with a huge team. So if you don't have a lot of data, can you still train CNNs? And the short answer is yes, you can, but you need to be a little bit smart with how you do it. So I think maybe it was last lecture, we showed how the different filters in your CNN are sort of extracting different types of features. So this goes back to someone asked about like the hierarchy of features in convolutional neural networks. So at the beginning, it's more of just like edges or patterns or really small shapes. And then at the highest level, you can imagine if we put an image into our CNN and we get this final vector right before we get our class scores, and we compare that to other images in our data set, you'll actually see that these values of the vector of our image are actually really close. So this is sort of like, you can think of this as sort of like the nearest neighbors thing we did before. But instead of it being the pixels of the image, we're looking at the vector at the very end of your CNN, right before you have the classification layer. So this would be like the 4096 or the 2048 layer. And if we look at the difference here is the L2 distance, you'll find that for a given image, if you put it into your model and you look at the other images that are close to the model in this vector space right here after you go through all the layers except the last one, that you'll find the images are extremely close to each other when the items are in the same category. So intuitively, what this basically means is that these features here are actually really good at you could build a linear classifier on top of them and then be able to, or a k-nearest neighbor classifier, and be able to classify objects extremely well. So how could you use this in practice? So what you would do is you would first train your model on ImageNet, or you would just grab a model someone else has trained on ImageNet or one of these really large web internet scale data sets, and you can just freeze all of these layers so you don't train any of them, you keep them exactly the same as before, and you replace this final layer, instead of it being, in the case of ImageNet, 1,000 classes, you replace it with the number of classes you have in your data set. And then when you're training the model, you only train this layer here. So if we think about, we talked about how there, sort of in the old paradigm of computer vision, you had feature extractors, which was a predefined set of operations to get stuff like color histograms and other predefined features. You can almost think of the frozen model as doing this. It's a predefined feature extractor that we're not changing in any way, but we're using it to calculate features that we then train a model on top of. It's actually extremely similar under that paradigm because you're not training it here. And if you have a larger data set, what tends to work best in practice is to actually train the whole model, but you're initializing it from these values that were pre-trained, say, on ImageNet or some other really large internet scale data set. So I think pretty much for all of the problems I ever work on, I'm doing this step 3 here because I have maybe 1 million or 10 million training examples. So I'll start it with a model that was trained on billions that I don't have the compute for, and then I'll fine tune the model on my relatively smaller data set, and I'll get better performance than if I just try to train a model myself, because the model's basically seen more data. It's created a better feature extractor, and then when I fine tune the whole thing, it can still be specific enough to my problem. You're basically taking, say, let's use a very concrete case where we're training a model on ImageNet. We're taking this model and we're replacing the final layer so that it's no longer outputting 1,000 classes. It's outputting, the number of classes in your data set. And we're initializing this randomly using the chiming initialization we talked about before. But the rest of these layers are maintaining their values that they had before. So we're not changing these values. And during gradient descent, we're never changing these values. So these values are unchanged. We basically take our image, we pass it through our model, and now it's just like it's almost like you're just training a linear classifier, where your input are these 4096 vectors for each image that we calculate by passing it through the whole model. Then we have our vector of 4096, and we're just mapping that to the number of classes. And we're only training this mapping at the end. Yeah, so the question is, will you have some bias in your model because it was trained on ImageNet? And the answer is definitely. So the model, if you do this number 2, like this way of training, then it will do best on data sets that look very similar to ImageNet. So these would be like pictures of everyday things like laptops or maybe a classroom or a person, things like this, where ImageNet is everyday objects. But if it was, say, photos of Mars, it would do a lot worse. So there's definitely bias based on the training data of the pre-trained model. And you want to get something that is in the same type of distribution, where you're seeing the same kinds of objects or locations or things like that. So the question is, what do you do when your data set is out of distribution? I actually have a slide here to cover some of that, so it's a great question. If you have a very similar data set but very little data, you can use the linear classifier strategy we just mentioned. If you have a similar data set, quite a lot of data, you'll get best performance by fine-tuning all the layers. These are strategies 2 and 3 on the slide that I mentioned earlier. But what about when you have a very different data set? So, if you have a lot of data, you might just want to start from scratch, or you might get better performance if you still initialize. Here you would test, but there's no guaranteed way to know that performance would be better or worse. And then, if you have very little data or a very different data set, you probably want to try to find a model that's trained on something close. There are specific techniques that researchers have looked into for out-of-domain generalization and, this basic idea of you have one domain, you train a model on one domain, and you're trying to learn a new domain that's different in some ways. So this is an active area of research, but I wouldn't say there's like a general technique that always works, and it's a bit problem dependent in that setting. Whereas this is for everything except the upper right quadrant here, it works pretty well in practice. So there are actually techniques for this, and it's a pretty active area of research, and certain models generalize better. Like I think language models are pretty good at learning a lot of different domains, for example. But yeah, it's definitely the worst scenario to be in, where you have a completely different problem that anyone's ever worked on before and you don't have a lot of data. It's by far the hardest to train a model in that setting. So the question is, do you ever do anything between training one final layer and all layers? Yeah, people have actually done a lot of work looking into training a subset of the layers. There's also a technique called LoRa, which we might go into in the Transformers lecture. I'm not sure if it'll make it this year, but the basic idea is to fine-tune all the layers in a way where you're not changing all the values exactly, but you're learning basically low-rank differences between the different layers, where you're sort of fine-tuning differences between the original layers rather than fine-tuning the layers themselves. So there's techniques. You could use LoRa. It would need more explanation, but the basic idea is instead of fine-tuning the actual values, you're fine-tuning these differences between the value layers, sort of like how a ResNet, you're learning the difference. LoRa's are like that, but you do it with a very small number of parameters. I think the question is, how did they basically decide how many layers to pick? Why did they pick a large number of layers? Specifically, why are there two convolution layers of each size instead of one? So it's actually really similar to the example we showed earlier with VGG, where if you have 3 of these 3x3 convolutions, you're able to have the same receptive field as a 7x7 convolution, but you're able to model more nonlinear relationships because you have these 3 activation functions rather than just one activation on the 7x7 filter. So basically, 3x3 is more expressive, but you're still looking at the same set of values as long as you have enough of them. So a larger set of smaller filters is more expressive than a smaller set of larger filters. Okay. So we'll go on. Basically try to find a large data set that has similar data, get a model that was trained on that, and then fine tune it on your own data. There's some good links. PyTorch image models has a bunch of models that are trained on ImageNet and other data sets. And then also just in the PyTorch Vision, a GitHub repo, you'll find some too. Okay, I'll talk over very briefly at the end for hyperparameter selection. So if you're having difficulty training your model and it's not working right away, I think the best thing you can do is to overfit on a small sample. So this is like the default debugging strategy in deep learning, where you just have one data point and you want to see your training loss basically go to 0. Your model should be able to memorize one training example. And if it's not able to do that, you have a bug somewhere in your code, or you're not picking the right kind of model to model your problem. So this is a really good training problem, and it'll also tell you like what learning rates work or what ones don't work, and you'll get a rough idea of the neighborhood of learning rates you should explore. So this is a good way to make sure your model's correct, make sure your learning rate is reasonable, and also to make sure you don't have any other bugs that could be impacting your code. So this is like always step 1. If you're having issues just running some code, this is how you debug. The second thing you would want to do after you get this is maybe you try a very coarse grid of hyperparameters. So I would first try with different learning rates and see how, if you train model on different learning rates, what are the training losses look like. You want one that has the most sustained decreasing in the training loss over maybe one epoch. That's like a pretty good estimation, but you can train for longer. Once you get a good set of learning rates, you could then look into other hyperparameters too. And specifically, besides the loss, you'll also want to look at the accuracy curves. So you have your training accuracy and your validation accuracy. If they're still going up, it means you want to keep training, pretty reasonable. But you might have a scenario where the training loss is going up, but your validation loss is going down. This is overfitting. So we need to either increase the regularization, or if we can get more data, that could also work. But you need to do one of the two in order to improve your performance further beyond the peak right here, I guess, would be the best model you have so far. if you're seeing very little of a gap here, then you can probably train for model for longer, because generally you do want to just get to the point where your validation loss has been maximized. So if you could just keep training, you can keep training. So even if there's not a significant gap here or anything, if you see the validation loss is similar to the the validation accuracy is similar to the training accuracy, you can probably keep training until your training accuracy starts diverging from your validation accuracy. And you really basically can repeat this process over and over again. One final note is in terms of for hyperparameter search, normally people think, you have 2 hyperparameters or more that you're searching over. Should you try every combination of the hyperparameters, or what is the best way to do it? I think in practice, random search over the hyperparameter space works a lot better than a grid search where you're trying every set of a predefined set. And the reason is mainly because you can imagine you have one axis, which is an unimportant hyperparameter, where depending on the value, your performance will be roughly the same, versus an important one. If you do random values across all of these, you'll actually search the hyperparameter space of your important parameter much more thoroughly, whereas you're sort of wasting time doing on the grid search, rechecking multiple values for an unimportant hyperparameter. So in practice, you should define the ranges you want to try and then just randomly collect hyperparameters with values from those ranges. And that's probably the best way to do it. And you just keep running till you get the best model. Okay, that's it. So we talked about layers and CNNs, activation functions, CNN architectures, and weight initialization. How do you actually predefine and build these models? And then we talked about how do you actually train it? How do you change your data to be input to the model? How do you augment it? Transfer learning is a really neat trick for improving performance. And then how do you pick the best hyperparameters? So, we covered a lot in lecture today. Thank you all so much.